Hello everyone and welcome to our first recitation. This is your teaching assistant Wasim Ramadan. Today we will be solving the first problem set. So let's get started. First of all, let me start by sharing my screen. All right. Now in problem set number 1, as we can see in here, I'll expand my screen. So first of all, we know we have problem number 1 and 2. I'll be skipping those. You can solve them by yourself. They are mainly based on revision. So I will jump into problem number 3 first of all. Now reading the question says, number 3, calculate design tensile strength and allowable tensile strength based on yield of gross section and fracture of net section. So, all right, let me choose my pointer. So in here we have this member, or you can call it as a connection. It consists of 2 plates on top, one plate on top and one plate at the bottom, and there is one in between both of these. Now, as we can see, these plates are connected by bolts, and in this problem we are given all the dimensions for the plates, we are given the spacing for the bolts, and we have everything necessary for the material. As we can see here, we are given the steel information. And also we have the bolt diameter. They are 16 millimeter in size. Also, we have, as we can see here in the problem, that those plates, as they are connected, and as we are supposed to calculate the tensile strength, first of all, as you can see, we have here one plate at the top and one plate at the bottom. I'm taking like a part of these, and here we have one in between. So when it comes to deciding the tensile strength of this connection, I have to choose the weakest link. Now, as you know, the more material you have, the higher resistance you have. And based on that logic, I will be picking up the weakest link. So the weakest plate we have over here, if we take a look, the upper plate, if we apply a force over here, it means that when you apply this force, it will be actually resisted by the plates at the bottom in the opposite direction. And each of those will take half of that force. So half phi Pn at top and half phi Pn at bottom. Now, based on that, we have the forces distributed. We can take a look now at the dimensions or the gross area. So if we take a look at this plate in the middle, we can see that the width of it is 300. And also the plates at the top and bottom, both of them have a width of 300. So these are the same. But what differs is that the thickness of one plate, for instance, the one in the middle is 10 millimeters. Now at the one at the bottom is 8 millimeters. So when it comes to deciding which one is weakest, we can see that the ones at top and bottom are weak. But because each one of the plates at top and bottom take half force, that doesn't mean that they are weakest. And that means that the one at risk is the one in the middle. Why? Because the area is slightly higher than the plates at top and bottom. As you can see here, it's 10 millimeter. And also we have one force, a whole force is applied to that plate. Therefore, this is the weakest link, we can say. Based on that, we can jump into our solution. Now, first of all, you have to check your yield of gross section, which means that there is a possibility that this piece in the middle might yield from such a point like this, as you apply the force in this direction. So in order to find the yield of cross section, we calculate it based on the equation that is shown over here. Now, as you can see, phi Pn, we want to find that. We have phi is equal to 0.9. This is the sort of like a factor of safety. We have Ag. Ag is the gross area, and we have the yield strength of the steel, Fy. So when it comes to calculating this, we have again 0.9, and we can calculate the gross area by multiplying 300 by 10. As we said, this is the link that is in danger of losing the capacity completely and failing. And also we are given the material strength, 275 in yield. So if we multiply those numbers, we get the yield of gross section to be equal to 742.5 kilonewtons based on LR of D. Now that's for the yield of gross section. Now there is a possibility that this member might have a net rupture because it is connected using bolts. Therefore, we might have net rupture. So for the net rupture, we have this equation here, phi Pn, again, the reduction factor multiplied by the force. Again, we have the reduction factor here, or the factor of safety. We have F ultimate, and we have the effective area. So in order to calculate, first of all, the effective area, we have to consider this equation. AE, the effective area, is equal to the reduction factor multiplied by the net area. Now, let's calculate at the beginning the shear lag, U. So how would you do that? First of all, you have to go to AISC table that is provided in AutoClass. In AISC table D3.1, if we take a look at here, we can calculate the shear lag from such a table. So we have multiple cases. We are supposed to look at all the cases. At the beginning, it might be strange to you, but once you solve problems, it will get easier. You don't have to go through it all the time. Now, if we read each case and decide which one fits our condition, we realize that case number 1 fits the condition. Why? Because in the description, it says all tension members where the tension load is transmitted directly to each of the cross-sectional elements by fasteners or welds. Now, except in case 4 and 5 and 6, if we take a look at them, in case 6, for example, it says rectangular HSS. We don't have such a member like this. If we take a look at case number 4, plates, angles, channels with welds at heels, we don't have any welds. So this is neglected. If we take a look at number 5, case number 5, it says round HSS. Also, we don't have that case. So obviously it's case number 1. And based on that, we take the shear lag to be equal as 1.0. So from here, the shear lag I found to be 1.0 exactly. Now I have to calculate the net area. So when it comes to the net area, I have to consider such an equation like this, which says the gross area minus the number of bolts multiplied by the thickness multiplied by the diameter of each hole. Also, if we had any staggering between the bolts, we consider S squared divided by 4G and multiplied by the thickness of the plate. Now, we have a case number 1 where the failure might take place. So if we take a look back again at the member or the connection we have, let me raise this first. Okay, so if we consider such a failure in the net rupture, there is a possibility that the failure might take place at the bolts in here, from the beginning till the end. So what happens is that this member at the middle might come out and the cut might be in here. So how would I calculate the net area? First of all, you take the gross area, 300 by 10, as we did previously, and minus the number of bolts. As you can see here, I'm losing 3 bolts. So minus 3 multiplied by 10, again 10 is the thickness of the plate, multiplied by 16 plus 4. Now, what's that? 16 is the size of the bolt, as we saw previously, M16 bolts, plus 4, which comes from the extra size of the hole, because we cannot have a hole that is equal to 16 exactly. You cannot put a bolt inside a hole that is 16 millimeters. We need extra spacing, and that extra spacing is equal to 4. Now, in order to find that spacing, we can go to AIC again, page number 41. There is a table that is guiding us regarding the nominal hole dimensions. So in table J3.3M, here it says the bolt diameter, for example, in our case, it is M16. The standard diameter for the hole dimensions, standard is 18, so plus 2, or you can have oversized hole, which is equal to 20. And based on that, I'm taking oversized hole diameter. So 16 plus 4 equals 20. And that's how I calculate this. Now, if we calculate the net area in this case, number 1, it appears that the net area for this case equal to 2,400 millimeters square. Now, there is another possibility. The failure might not take place in that in those 3 bolts. It might take a different path. So if we erase this and consider a different path for failure, the failure might look like this. It might go from here, cut from there, go back again, here, there, and go out at the end. Now, as you can see here, in this case, I'm losing 5 bolts. So in this case, I'm losing 5 bolts. And going back again to this equation, in order to calculate AN, first of all, I will start with A gross. So here I'm calculating A gross, 300 multiplied by 10. Then, as I said before, I have 5 bolts that will be cut. So minus 5 multiplied by the 10, which is the thickness of the plate, and multiplied by the size of the hole, or the diameter of the hole, which is 16 plus 4. Now, because we have a staggering, the staggering, as we can see here, is the inclined line. So when the failure is actually not perpendicular to the force, but it is inclined, that adds extra area. So in order to take it into consideration, we take a plus sign. Be careful about this. Here we have a plus sign, here we have minus sign. So plus, how many staggers you have? We have one side here, 2, 3, and 4. So I have 4 staggerings. So plus 4 multiplied by S square. What's S square? S square is the distance between this bolt, for instance, and the next bolt. The distance is parallel to the force. So it is 60 squared divided by 4 multiplied by G. Now G is perpendicular distance between the bolts. So the distance from this bolt to the other bolt, this one in here, is 50 millimeters. So that's why I'm multiplying 4 by 50. And at the end, do not forget to multiply by the thickness of the plate, which is 10. Now from here, if you calculate this, the net area appears to be 2,720 millimeters. Now we have 2 cases. We have case number 2, says 5 bolts. The area appears to be, the net area appears to be 2,720 millimeters. And case number 1, 3 bolts, it appears that the net area would be 2,400 millimeters. Now, in order to proceed and calculate the net rupture from this equation, I have to choose the lowest net area, the lowest effective area. So when you make a comparison between those 2 cases, you realize that case number 1 is the riskiest one. So case number 1, low capacity, because the net area is lower than case number 2. And based on that, I'm substituting now. So First of all, we have the reduction factor for the net rupture is equal to 0.75 according to LRFD. Notice that here it is 0.75 for the net rupture, but it is 0.9 for the yield of gross section. Now for the F ultimate, Fu is given to us as 430 megapascal multiplied by 1, which is the shear lag we found previously, which is U. And lastly, multiplied by the net area, 2,400 millimeters. Now, if you multiply all those numbers, you will obtain the force or the capacity of this plate to be equal to 774 kilonewtons. Now, by that, you have solved this problem. And also, there is another comparison we have to make. Sorry about that. So we have found actually the capacity for the member and the net rupture to be equal to 774 in here. And also we have found the capacity of the member for the yield of gross to be 742.5. So which one is actually the capacity of this member? I have to compare between the capacity in the yield of gross section and the capacity of the net rupture. So when I do that and I compare between both of these values, I realize that the plate would fail in yield of gross. And therefore, actually, the capacity of this plate is equal to 742.5. 742.5 is lower than 774 in net rupture case. And therefore, I have to be on the safe side and pick the lowest value. All right, now moving on to problem number 4. In this problem, we are supposed to calculate design tensile strength and allowable tensile strength based on yield of gross section and fracture of net section. Assume that gusset plate is okay. So in this problem, as we can see here, we are given the cross section for UPN 320. This UPN 320 is connected to a gusset plate. This is the gusset plate we have in here. And according to the problem, it says, assume that the gusset plate is okay. So we have to check the capacity of UPN 320. Now, this member, as we can see here, it's connected using bolts, and there is a force that is applied. Also, we are given all the information for the steel, the yielding capacity of this steel material, and the ultimate strength, 510 megapascal, and we are also given the bolt's diameter. So in order to solve this problem, first of all, as we did before, we have to consider the yield of gross section. So we go back again to the equation we know. The Pn, or the capacity of this member, would be equal to Ag multiplied by Fy. Now, what's Ag? The gross area for UPN 320. It is 7,600 millimeters. How did I know that? If you go back to this section or the tables that are provided in OptoClass, you will find that UPN 320 okay, so here we have the UPN. Now, in here we can see that the UPN in page number 3, UPN 320, if we take a look at this column, A, which means area, it says 76 centimeters square. Now, I convert it to millimeters square, which is basically by multiplying by 100. So from here, I'm saying that the gross area is equal to 7,600. Now I can calculate the yield of gross section from here. So basically I substitute 7,600 multiplied by the yielding capacity of the steel, 355 megapascal. And based on that, I get the capacity in the yield of gross section to be equal to 2,698 kilonewtons. Now, use the reduction factor according to LRFD or ASD. So for example, according to LRFD, we multiply by 0.9. So I'm multiplying the value that I obtained by 0.9, And from here, I would say that the actual capacity of the member is 2,430 for the case of field of cross-section. Now, we have to also consider the net rupture since this member is connected with the bolts. So I'm going back again to the equation that we saw previously. Pn is equal to F ultimate multiplied by AE, effective area. And AE again is equal to shear lag multiplied by the net area. Now, in order to calculate the shear lag, as I told you, we have to go to the tables that are provided in AISC and the table that we have for the shear lag. I think, okay, we can search for it. All right, so in page number 13, we have this table again. So the case we had UPN 320. Now, if we go to and read the cases, if we read case number 1, it wouldn't apply. If we take a look at case number 2, it says all tension members except HSS, where the tension load is transmitted to some but not all of the cross-sectional elements by fasteners or by longitudinal wells. And also we have case number 7 is permitted for the wide flange, MS and HP shapes. For angles, case number 8 is permitted to be used. So if you take a look at other cases, you realize that case number 2 is fitting our condition. And from here, I can calculate the shear lag based on this equation, which is U is equal to 1 minus X bar divided by L. So here is the equation, 1 minus X bar over L. How would I find X bar? So first of all, X bar is actually the distance where the member is connected to the centroid of the member that you have, UPN 320. Now, in order to get that X bar, you go back again to the tables that are provided to you, and we take a look at UPN 320. So what am I going to look at? I want the value for the centroid. I want to find the centroid of UPN 320. And for that case, I'm taking a look at XS. XS is showing us the centroid of UPN 320, which is 2.6 centimeters. Now for our case, I took it as 26 millimeters. Also, we have to find L. What is L? L basically is the length from the first bolt to the last bolt in parallel to load direction. So to show you L, go back again to the problem. Here we can see that the bolts are connected. Here is the first bolt, and here is the last bolt. Now the distance between them is equal to 100 millimeters exactly. So that is my L value. I substitute it in this equation, calculate it, and get my U to be equal to 0.74. So U is calculated in here, U is equal to 0.74. Now, since I have U, I have to find the net area. So what's again the net area? It's based on this equation. This is how you calculate it. So first of all, we have to consider some cases. Initially, I'm considering that there will be a cut over here. The member will face net rupture in here. And that means in case number 1, I would lose 3 bolts. So we substitute now our values. First of all, we have the gross area, 7,600 from the sections table. And then minus the number of bolts, 3, multiplied by 20. 20 is, again, the whole size, 16 plus 4, multiplied by 14. Now, what's that 14? 14 is the thickness of UPN 320 web, which is denoted by TW. TW means the thickness of the web. Why did I take the web? Because the bolts are connected in the web of UPN 320. Again, if you want to find TW, you go to the sections. So for UPN 320, I'm checking over here. TW, it says 14. And because of that, I substitute 14 over here. So if you calculate this, you will obtain the net area to be equal to 6,760 millimeters square. Now, there might be another case where we have a different path for the failure. So what's that path? The path of failure might take place in here. Goes into this bolt, move to this bolt, this one, that one, and the last bolt over here, and that's it. Now, as you realize, I included all bolts. I didn't have any bolts remaining in the body of UPN 320. I considered all of them. So now, as you can see here, I have reduction of 5 bolts. That's my path for case number 2. So in order to calculate now the net area for such a path of failure, again, the gross area, 7,600 millimeters square, minus the number of bolts, 5, I'm losing 5 bolts, multiplied by 20, which is 16 plus 4, that is the whole diameter, multiplied by 14. Again, 14 is the thickness of the web. Plus now we have a staggering. So that's the staggering part that we have to take into account. Now, how many staggering do I have? I have one in here, another one there, 3 and 4 staggerings. Now for the staggering, plus 4 multiplied by, what is S? S is the parallel distance to the force between the bolts. It is equal to 50 squared, and divided by 4 multiplied by G. Again, G is the perpendicular distance between such bolts of staggering. Now this is crowded. Let me erase. So I'm drawing the path again. Now G value is the distance, for example, between this bolt and that bolt, which is equal to 60 as it's given to us in here. So I'm substituting 4 by 60. And don't forget, multiply by the thickness of the web. So again, 14 is the thickness of the web. Now, if you calculate all of this, you will get the net area to be equal to 6,783 millimeters square. Now, I have 2 cases. I don't think that a failure is in any other paths. So I'm sticking to only those 2 cases. Now I have to compare which area is the smallest. As you can see here, in case number 1, we have the smallest net area. So I will proceed with it. Now, hence, case number 1 is critical because the net area here is smallest. And I can calculate now the effective area. AE is equal to the shear lag we found previously, U, 0.74, multiplied by the net area, 6,760. Now multiply all of those, you get your effective area to be equal to 5,002.4 millimeters square. Now we can calculate the net rupture capacity, or the capacity of the member based on the net rupture. Pn is equal to 510, which is F ultimate. I'm using this equation. F ultimate is 510 megapascal multiplied by 5,002.4 millimeters square, and I would get Pn equal to 2,501.2 kilonewtons. I have to multiply by the reduction factor 0.75 according to LRFD, and I get from here the capacity of the member to be equal to 1,913.4 kilonewtons. Now that's for the net rupture. We are not done yet. We have to make the final comparison in order to decide what is the actual capacity of this member. And therefore, I compare between the net rupture and the yield of gross section. So previously, we found that the yield of gross section is equal to 2,430, and the net rupture is equal to 1,913.4. So which one is smallest? Obviously, the net rupture. And based on that, I say that the design tensile strength is 1913.4 kilonewtons. That's my limit. If I exceed this value, that means that my member will fail in net rupture in case number one. Case number one, if you remember, it was taking 3 bolts only in here. And that's it for this problem. Problem number 5 in this problem set. Reading the question, it says first, compute the effective area, net area, AE, for the I-shaped tension members shown below. So first of all, we have part A. In this part, we are given IPN 300, and it is connected with 2 plate members. So we are considered with finding only the AE, the effective area for IPN 300 section. And we are also given the bolts diameter, and we have the spacing between those bolts. Now, as we can see, this wide flange is connected from top and bottom. If we take a look at the bolts, we have 3 bolts from this side, and we have 3 bolts from the other side. So in total, at top part, we have 6 bolts, and at the bottom, we have 6 bolts as well. Now, coming to the solution, first of all, as we know, in order to calculate the shear lag U, or in order to calculate AE, let me remind you, AE is equal to AN multiplied by U. U is the shear lag. So in order to calculate this shear lag, I go to the AISC. And going back to this table, reading the cases, first of all, I have the case that fits my needs, case number 2. Now, in this case, I have the wide flange, and I can use the equation that is given to me in here, 1 minus x bar divided by L. Now, notice that if the member or your tension member is connected with bolts from the top, you have to consider the x bar equal to half of this wide flange. You take a T shape. Now, how is that? It means basically that you have to cut your section into 2 pieces. And for instance, you can consider the upper piece. The upper piece would become a T shape. Now, remember again, because it's connected from top with bolts, I'm cutting the wide flange into 2 pieces. This case only applies to wide flanges. I cut it to 2 pieces, and it becomes a T shape. Now, I have then to consider the x bar. The x bar is the distance to the centroid of this T shape that I have now. So in order to calculate this x bar, you have to do it by yourself. Actually, you have to calculate it. I take all the dimensions that I need from the sections table. So the sections table that is provided to me in here, I find IPN 300. I can take, for instance, the flange width. It's given as 125. Here you can see it's 125. I have the thickness of the flange, 16.2. I have 150 for half of the depth. Notice that the whole depth of this section is equal to 300 in here. So since I cut the member into 2 pieces, I have to consider half of the depth, which is 150 millimeters. Now, as I have all those dimensions, I don't really need the upper part, this one, the gusset plate. So I'm just concerned with the T shape. I can calculate the x bar. Now, the x bar from here till the centroid. So what would it be? As you can see here, it's calculated. This is actually basics from statics. So you can do it by yourself. It's not a big deal. Now, after calculating the x bar, I'm substituting in the equation of the shear lag. As we said before, 1 minus x bar divided by L. So x bar appears to be equal to 39.33 from this equation over here, millimeters, of course, and divided by 150. Now, this 150 is the distance from the first bolt to the last bolt. So if we go back again and take a look at the drawing that we have in here, this is my first bolt. and this is my last bolt. And the distance in between them is 150. That's why I substitute 150 over here. Now, if we calculate this shear lag based on this case, it appears that U is equal to 0.738. Now, the shear lag is not calculated only from case number 2. Why? Because also there is another case that is possible for the shear lag. So if we read case number 2 carefully, it says, alternatively, case 7 is permitted for W or wide flange, MS and HP shapes. So if we go down to case number 7, in here, we can read the description. And if we take a look at this part, it says with flange connected with 3 or more fasteners. And the other part says with whip connected with 4 or more fasteners. So for our case, we actually have the bolts connected at the flange. Therefore, this applies. And in order to calculate the shear lag U, we take a look at here. So it says if BF is bigger than or equal to 2 over 3 or 2/3 of D, BF is the flange width, and D is the depth of the section. If this is the case, U would be equal to 0.9. Otherwise, U would be equal to 0.85. So if we check BF and 2/3 of the section depth, BF is equal to 125. And 2/3 of the depth, or 2/3 of 300, would be equal to 200. So which one is bigger, 200 or 125? Obviously, 2/3 of the depth is bigger, and therefore the shear lag would be equal to 0.85. So from case number 7, U is equal to 0.85. So now, as you can see, I have 2 shear lags. Which one am I supposed to use in order to calculate AE, the effective area? Well, I'm permitted to use the biggest value according to AIC. So now coming to the AN, the net area. In order to calculate the effective area, I have to calculate the net area. So in this case, as you know from the previous equation I show you, it's first of all, you have to start with the gross area. The gross area, we can find it from the sections table. For IPN 300, it is 6,900 millimeters square, and minus the bolts reduction. Now, if I consider the path that the failure might take, there is only one path, which is this one. The net rupture would occur in here, and therefore, I have the bolts reducing the gross area that I have. So if you remember, we had bolts connected from top and bottom. Now, as you can see here, if the path is taking place from here, there are 2 bolts that I'm losing. But because I have 2 other bolts at the bottom, I have bolts that will be cut from here and bolts from here. 2 and 2, I have 4 bolts that I'm losing. 2 at top and 2 at bottom. And therefore, minus 4 multiplied by 22 plus 4. So again, 22 plus 4 is actually the size of the hole. And then you multiply it by 16.2, which is the thickness of the flange. Since the bolts are connected in the flange in here for this member, therefore I have to consider the thickness of the flange, which is 16.2. If you calculate the net area from here, it appears that it is equal to 5,215 millimeters square. Now, since I have the shear lag and I have the net area, I can calculate the effective area. So plug in the values. AN 5,215 multiplied by 0.85. Again, you can pick the biggest shear lag. And in our case, it is 0.85. If you substitute all the values, it appears that the effective area is equal to 4,452.92 millimeters square. And that's the effective area for case A of this question. Now, if we take a look at case B or part B, in this part, instead of having the bolts connected at the flanges, we have them connected at the web. Now, also notice that the section has changed. It was IPN 300, now it became HEA 300. Now, from here, also I have the spacing between the bolts and I have the bolt size, etc. So as we did before, we go back again to the table that we have in AIC, and we take a look at the cases that we have. Now, if we take a look at the cases, first of all, case number 2 applies. And in our case, we can use this equation. But since, again, we have to find the X bar, but since the bolts are connected in the web, I have to cut my member into 2 pieces. But rather than having a T shape, remember I cut it last time in this way in here. Now this time I have to cut it vertically. And because of that, I would get a C shape. So this is a closer look. X bar would be the distance from here, from the middle of this section to the centroid of the C shape that I would have. So if you make a cut, of course, you will get a C shape. Now, if actually we calculate the X bar for that C shape, you basically take the C shape, you put all the dimensions that you need, you go to HEA in the section tables. So we had HEA 300, the table is HE 300A, there is no difference. So you take all the dimensions you need. You have the depth 290, you have the flange width 300, you take half of it. So this would be 150. The depth, as we said, is equal to 300. And you can put all the other dimensions. And then you can calculate the X bar, the distance to the centroid of this C shape that you have. Now, if you calculate X bar, you will get 59.76 millimeters. Also, if you remember, we have to divide by L. L is actually the distance between the first bolt and the last bolt. So here we have, this is the first bolt, we can say, and here is the last bolt. We have 360s. So 3 multiplied by 60, the distance is equal to 180. I'm substituting 180 over here. Now, if you calculate this, you get U equal to 0.668. Now, there is another case that applies for this part B of question 5, U from case number 7. So if we go back again to our AIC and take a look at case number 7, here it says the white flange shapes or T's cut. Here it said with flange connected with 3 or more fasteners per line in direction of loading, but we don't have the bolts connected in the flanges. We have them connected in the web, and with web connected with 4 or more fasteners. So if we take a look here, again, we have 1, 2, 3, and 4 bolts connected in the direction of loading. And because of that, we have the shear lag in this case equal to 0.7. So if you substitute that, going back over here, yeah. So U is equal to 0.7 in this case. Now I can calculate the net area. First of all, let me erase this. All right, so now this section is more clear. All right, so now when you have a cut, when you want to consider the net rupture, of course, you would have effective area, and in order to calculate the effective area, you would calculate the net area. So the only cut that we might face is taking a place like this, in the red line, as shown. So first of all, you have to consider the gross area for HEA 300. Sorry. And the gross area appears to be 11,200. Again, you can find that from this sections table, HEA 300. The A gross is equal to 112.5, but you can multiply by 100 in order to get it in millimeters. Minus 2 multiplied by, now why 2? Because of the number of bolts that I'm losing, multiplied by 22 plus 4. Now this is the whole diameter. And I have the web thickness. Since those bolts are connected in the web, I have to consider the web thickness, and it is equal to 8.5. Now from here, if we calculate the net area, it appears to be equal to 10,758 millimeters square. Now, as we have this net area, we can calculate the effective area. And if you remember, I said that you can, according to AISC, you're permitted to use the biggest shear lag. So from here, I take shear lag to be equal to 0.7 from case number 7, and multiplied by the net area that I found, 10,758. From here, the effective area appears to be 7,530.6 millimeters square.